Welcome back. Over the course of the next 6 lectures, we will introduce important properties of nucleus, which will be explained later in this course, the basis for these properties. So let's get started. So, an important discovery is by J.J. Thomson, who discovered that one of the fundamental particles of nature is the electron. He later developed the plum pudding model. So when Rutherford started his experiment, uh, this was our understanding of atom and matter. So what is Rutherford's experiment? So Rutherford had a source that emitted alpha particles. So this is the alpha particle emitter. If you have, let's say, lead blocks and with the hole, alpha particles come out in a narrow beam. And there is a foil of gold, a thin foil of gold. Um, and there are detectors at different positions. These are what are called scintillation detectors, in the sense that if the alpha particle hits the screen, there'll be light emission. So in a dark room, if you do this experiment, you would know where do these alpha particles that hit the gold foil will scatter off. So that is the kind of experiment. So when Rutherford did this experiment, most of the alpha particles went through the gold foil, which was uh, not surprising, in the sense that if most of the matter is, let's say, uh, net neutral based on this kind of model, you would think most of the alpha particles, which are positive in nature, will get through the gold foil. However, what was surprising was some of the alpha particle, not many, but very few of this alpha particles recoiled at great angles away from the linear trajectory. Okay, so this was what was very surprising. So he saw that, then he observed, and he inferred that um, a model in which uh, the center of the atom had a lot of positive charge, and the interaction between positively charged alpha particle and uh, a nucleus, which was at the center of atom, the repulsive interaction gave rise to this kind of scattering events. So that was an important discovery. So we will move on to different notations and classifications that are utilized for describing the nucleus. We'll see the reason for classifying. So if you have an element X, uh, this itself will tell you what is this element. So you will have atomic weight, atomic number. This minus this gives you the number of neutrons. For example, this is a chemical symbol, right? As soon as you see this, you know it's uranium. This is the atomic weight. This is the atomic number. So this is the number of protons in the nucleus, which determines the chemical properties, let's say uranium. And this minus this gives you the number of neutrons. So in in chemistry, what is important is just the atomic number, right? That determines the number of electrons surrounding the nucleus, which on the valence electrons determines the chemical properties. But in nuclear physics, both the atomic number and the number of neutrons are critical. In fact, the ratio of number of ratio is what matters, because you would see later that there are something called strong nuclear forces which operate between all nucleons. So let's understand what is the challenge here. So you have very densely packed, positively charged nucleus. Within the nucleus, there are just 92 protons in a very small confined region. So there is enormous amount of um, repulsion. However, there are, besides these electrodynamical forces that operate between charged objects, there are interactions between all nucleons, which are um, net attractive. It is attractive at very small distances. We'll elaborate this later, but just to set the context, we're mentioning this. So the strong nuclear forces operate not only between neutron and neutron, it also operates between neutron and proton and proton and proton. Okay, so this is operational only where they are near each other. So, in a way, that is the attractive interaction which acts against this repulsive electrodynamical interaction. So, if you have a lot of neutrons, you will see that is going to be disadvantageous. We'll see why in the next lecture. And if you have a lot of protons, you would also anticipate that there's going to be a lot of repulsive interaction, which is going to make the nucleus unstable. So essentially, both the number of protons and the number of neutrons are very critical to understand the properties of nucleus. So our classification scheme will try to bring out these features. So uh, right now we'll just state it. The isolated neutron is unstable. Even though it's neutral, if you have just a neutron, it always decays to a proton and an electron and something more. But this what is important, it decays to proton and electron. So compared to an isolated proton, these two are more stable. So the half-life of a neutron, isolated neutron, is about 10 minutes. It is different, half-life is different from mean lifetime, which is about 15 minutes. So in order to stabilize a neutron has to be present along, let's say, with a proton, okay? So for example, hydrogen doesn't have a neutron, but an isotope of hydrogen, that is deuterium, has one neutron and one proton. So because of the attractive interaction between the neutron and proton, this neutron in the deuterium atom can get stabilized, okay, and can exist, okay? So deuterium is not radioactive. So isolated neutron is unstable, but neutron can be stabilized in the presence of proton because of strong nuclear forces. So what are isotopes? Isotopes have the same atomic number. They are all hydrogen, but they differ in the number of neutrons present in the nucleus. No neutron, one neutron, and two neutron. These two are not radioactive naturally, but this is naturally radioactive. This is called tritium. So why is that? Why? Just let's think about this. So in all these three nucleus, there is only one positive charge. So you may ask why this is going to be radioactive. So that has to be seen from this fact, because neutron itself is not stable. As you keep increasing the number of neutrons in a nucleus, you are in a way increasing some part of the nucleus which is not that stable, right? You are increasing the number of neutrons, and the neutrons can get to a more stable proton and electron, right? So in a way, this is, if you have more neutrons, it will, some of the neutron is going to decay to a proton and an electron, which would increase the atomic number. So that is one kind of radioactive decay, let's say beta decay. We will see, elaborate on over this in the next few lectures. So you have isotopes of probably uranium. So there are two nuclear isotopes that are very important, isotopes of uranium and isotopes of hydrogen. We'll see why they're going to be important. This is important for nuclear energy, atomic bomb, and so on. This has given us a lot of fundamental understanding. So all these things have the same number of atomic number, but they differ in the number of neutrons. Then you have isobars. So here the atomic weight is the same atomic number. Therefore, the number of neutrons is also different. So why do we have this classification? Within this classification, the ratio of neutrons to proton is different. Therefore, the stability of this nucleus is also going to be different. Then you have isotones, right? Here you have three different elements, hydrogen, helium, and lithium, but all of them have two neutrons. It has 2 neutrons, 4 minus 2, 2, 5 minus 3, 2. So all these things have the same number of neutrons, but different protons. So if you look at the nucleus, the repulsive interaction between the protons is going to increase, but the number of neutrons are the same. So the way elements that have more number of protons, if the ratio of protons to neutrons increases, that also makes the nucleus unstable, and there's a different kind of radioactive decay. We'll see what that is in a later lecture. Then you have isomers. So nucleides which have same A and Z. For example, cobalt has these two different kinds of nucleides. In here, M indicates a metastable nuclei. So supposing you may reach this during nuclear radioactive decay, and this would further relax back to a more stable state. So you would see why there are metastable states and in what manner metastable state differs from the ground state in some later lecture. So, of course, isomeric states have measurable lifetime. That's what is important. You can isolate this and measure the lifetime of this nuclei. Okay, so that's the difference between just a collective excitation, which has high energy, and an excitation which is metastable. Metastable means it is in a local minima, not a global minima. You can measure the lifetime of this object. Then this object will emit a gamma photon and then go to this ground state. In the next lecture, we will introduce an important concept. This is very, very critical in thinking through nuclear properties. Mass and energy are more or less equivalent, and the way to think about mass is via thinking through energies. That'll be the topic for the next lecture. Thank you.